Welcome to our comprehensive video on independent current sources. In this tutorial, we will delve into the characteristics of both ideal and practical current sources, shedding light on their behavior and practical applications. Let's kick things off by examining the ideal current source. An ideal current source is a theoretical concept that serves as a valuable abstraction in circuit analysis and design. It represents a source that delivers a constant current, regardless of external conditions or variations. The ideal current source is commonly depicted using a symbol consisting of an arrow indicating the direction of current flow. In this idealized model, the internal resistance, denoted as RSH, is assumed to be infinite, effectively implying that it has no impact on the output current. We symbolize the current provided by the ideal source as I. To gain a visual understanding of the characteristics of an ideal current source, let's construct a graph that relates the load resistance, RL, to the output current, IT. By plotting RL on the x-axis and IT on the y-axis, we can examine how the current source behaves under different load conditions. Since the internal resistance is infinite in the ideal model, the output current remains constant, irrespective of the load resistance. Consequently, the graph appears as a horizontal line parallel to the x-axis, indicating a consistent output current I for any value of RL. This feature is the defining quality of an ideal current source. It can deliver a specified current regardless of the external load to which it is connected. However, real-world current sources possess internal resistances, although often relatively large. These internal resistances have a discernible influence on the output current, resulting in variations. To account for this, we introduce the practical current source, which encompasses the ideal current source in series with an internal resistance, RSH. To represent the characteristics of a practical current source, let's create a graph similar to the one for the ideal source. Here, we plot RL on the x-axis and IT on the y-axis. Unlike the ideal model, the output current of a practical current source fluctuates depending on the load resistance and the internal resistance. As the load resistance increases, the output current decreases due to the voltage drop across the internal resistance. Consequently, the graph exhibits a declining slope, signifying a reduction in the output current as RL increases. This behavior arises from the fact that the internal resistance restricts the flow of current, resulting in a diminished output as the load resistance increases. In addition to affecting the output current, the internal resistance of a practical current source also impacts the terminal voltage, denoted as VT. As the output current decreases with higher RL values, the terminal voltage experiences a proportional decline. This relationship can be explained using Ohm's law, VT equals at asterisk RL plus RSH, where the terminal voltage equals the product of the output current and the sum of the load resistance and the internal resistance. Thus, the terminal voltage decreases as the output current diminishes due to the combined effects of RL and RSH. Understanding the characteristics of practical current sources is crucial for circuit analysis and design, as it enables engineers to consider the influence of internal resistance on overall circuit performance. By accurately modeling and accounting for these variations, circuit designers can optimize their designs for specific operating conditions, ensuring reliable and efficient operation. To summarize, while an ideal current source delivers a constant output current irrespective of the load resistance, a practical current source exhibits variations in the output current due to its internal resistance. By comprehending these characteristics, engineers can effectively design and analyze circuits using independent current sources, guaranteeing reliable and efficient operation across a wide range of applications.